thanks for joining. I'm going to be talking about, well, the title is Time Across Null Horizons. So the main idea of the talk is that when you construct a globally regular time coordinate across the space-time, that coordinate can be interpreted as being hyperboloidal. So this image is, I like this image a lot. This is by the Dutch graphic artist MC Escher from 1959, where he demonstrates the conformal disk model. It's like a tessellation of infinitely intertwined angels and demons. It's called Heaven and Hell. And it somehow reminds you maybe of a black hole horizon. And also it might remind you of like one of these cosmological pictures where you have a logarithmic scale. At the center is the Earth, and then the farther you go, the larger structures appear. And it's intentional in a way because these are things that I will both talk about, the cosmological horizons and the black hole horizons, and then I'm going to connect that to the asymptotically flat case. So in terms of the takeaway message, the message of the talk is really single sentence. It's very short. My main argument is that horizon penetrating time is hyperboloidal. This will be obvious to some of you. For others, it might be new. So there is no new results in this talk. It's more like a viewpoint of how we can understand hyperboloidal coordinates in Lorentzian manifolds. And I hope that this presentation will make it clear that hyperboloidal coordinates are very natural in Lorentzian manifolds, as natural as spherical coordinates are in Riemannian manifolds. And in fact, this is me trying to counteract this perception in relativity, mathematical and numerical relativity, that hyperboloidal coordinates are somewhat weird. It's a niche topic. Well, it is a niche topic, but I think it's very fundamental to Lorentzian manifolds. So the structure of the talk, I'm going to first start explaining what I mean by hyperboloids, space-time hyperboloids. As pseudospheres in Minkowski space, just connecting to the spherical analogy in Riemannian manifolds, how hyperbolic geometry appears from that. Then I will talk about horizons, so both event horizons and cosmological horizons, and some historical overview of how horizon penetrating coordinates have been constructed, and then connect that to regularization of null infinity by space and time coordinates. All right, so this is one of my favorite quotes by Minkowski. He gave an address in 1908 in Köln to a collection of natural scientists, where he declared, this idea of space-time. So henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve independence. This is, of course, German 19th, 20th century romantic language, a little bit exaggerated, if you will, a little bit optimistic. And the reason why I say that is because obviously space by itself and time by itself have not faded away into mere shadows. We still use them. Like if you browse the archive for relativity papers, not everybody, but many people still use space and time. In black hole perturbation theory, space and time separately appears. Space-time splitting is needed for certain mathematical proofs, but we still have a kind of the union that plays a role. And in this particular talk, that union will be of a specific form, and that also appeared in this talk in 1908. Right? This is more than 100 years old. And in the first talk that Minkowski gave, he actually talked about the space-time hyperboloid. So the history of hyperboloidal foliations, if you will, goes back to, it's connected to the history of space-time. It's as old as the idea of space-time itself. So on the left is a drawing by Minkowski. I forgot to maybe put a spotlight here. So here's a drawing by Minkowski. This is his attempt to explain the quadratic form, the Minkowski metric that we call today, and what it means in terms of space and time coordinates. And here you have essentially the unit circle in Minkowski spacetime, which is invariant under Lorentz transformation. So here's the hyperboloid. It asymptotes to the future null cone. I have a cleaner picture of this here with the null cone and the hyperboloid. This is the space-like future hyperboloid, and it's invariant under Lorentz transformations. And it's a fundamental object because it's the set of points at unit proper time from the origin, or the set of events at proper time from the origin. So if you imagine you send out, let's say, graviton with a finite survival time, or inertial observers going out from the origin in every distance, and then they take a snapshot at unit proper time. This is the surface that connects that snapshot. So it's the analog of a circle in Minkowski space. We call it pseudocircle. In higher dimensions, you call it pseudosphere. And it turns out, if you just really look at that set, it has 4 components. This red component is the future space-like component. Then you get 2 time-like components and a past space-like component. The time-like components are also important. You know, when you talk about Rindler space-time, that's exactly what it is. It represents observers at constant acceleration. And if you draw this in the Penrose diagram, what you get is a square. This is like a neat little factoid. If you take the unit circle in Minkowski space and draw it in the Penrose diagram, you get a unit square. And again, it has these 4 parts, and then we're interested in the part that's in the future of the future light cone, and it's space-like, right? So this is t equals square root of 1 plus x squared. If you go to higher dimensions, what you get is, from this hyperbola, from this pseudocircle, you get a hyperboloid or a pseudosphere. And that's independent of relativity. You know, this is how people sometimes introduce hyperbolic geometry. You take the Minkowski space, you embed the unit hyperboloid into the Minkowski space, and then you define some intrinsic coordinates using hyperbolic trigonometry, you know, hyperbolic functions. And then the metric you get is the metric on the hyperboloid, which is the metric of a space of constant negative mean curvature. So hyperbolic geometry. That's how you can drive it, even if you don't want to deal with relativity. This is how sometimes people do this. And this geometry is, in fact, also the geometry of my title image. Now, this hyperboloid model is an open space. It expands to infinity. But if you want to map it to a finite space, this is what you get. This is known as also as the Poincaré disk model of hyperbolic geometry. But it's actually due to Riemann and Beltrami in 1868. So this is mapping of that hyperboloid by just a simple compactification to a finite disk. And Escher came across this through Coxeter in 1950s, and then he drew this tessellation. There's a very interesting story of how he came to draw this tessellation of angels and demons, and how that connects to actually the Penrose diagrams. So Escher knew Penrose. Penrose actually visited Escher in 1962. And I think this may have been an inspiration for the Penrose diagrams, because if you look at this boundary of the hyperbolic geometry, it's called the ideal boundary in differential geometry. That's a cut of scry, right? And I will show that to you in terms of the Minkowski space. If you do hyperboloidal foliation, this boundary is essentially a cut of scry. It's where the idealized observers are. So ideal boundary is a very appropriate term for it. Okay, so this is just Minkowski space. I think I talked about what I mean by pseudospheres and how the hyperbolic geometry comes about, and the central role of the hyperboloid in Minkowski space as the set of points equidistant from the origin. So now I'm going to switch on gravitation and then do a little historical overview of the idea of horizons, event horizon and cosmological horizon, and how that connects to the construction of a regular time code. All right, so it starts with Schwarzschild's discovery of the spherical symmetric solution to Einstein's equations, the Schwarzschild metric. And of course, the Schwarzschild metric has this singularity because this factor f vanishes there at r equals 2m. We know this to be the event horizon, but there was almost a half a century confusion about the meaning of this magic sphere. It was called the magic sphere by Eddington. So on the right is a diagram. It's sort of a conformal diagram, if you will, of outgoing and incoming null rays. And as you can see, there's a pileup of these null rays at r equals 2m. And this is where the coordinate velocities of this characteristic vanish on the grid, on the Schwarzschild grid. In 1921 and 1922, Gulstand and Painlevé, they came up both around the same time with a description of the Schwarzschild metric, which is regular across the event horizon. So here you see that the incoming light rays pass smoothly across the event horizon, and this is also spatially flat. So it's spatially flat because it is adapted to freely falling observers. And as you can see, the incoming characteristic speed does not vanish there at the horizon. So the horizon is actually a regular point of this metric. There is no singularity of this metric, and it's spatially flat with this definition of time. I will get back to this spatial flat construction in other geometries. But at that time, it wasn't recognized that this was really the Schwarzschild geometry, and this was just the magic sphere was just a coordinate singularity. It took much longer. And in fact, you can see here Eddington and Finkelstein. The Eddington-Finkelstein coordinates somehow span a time range of 34 years. And the reason is that when Eddington wrote this metric, it was also not clear to him that this just showed that the Schwarzschild singularity was actually not a real singularity. It's just it was a coordinate singularity. So the Eddington-Finkelstein construction is what I call a characteristic preserving construction. You get the characteristics with respect to the tortoise coordinate. And remember, the domain of the tortoise coordinate is infinite, right? This spans from minus infinity to plus infinity, and minus infinity corresponds to the event horizon. And then you require that the new time coordinate, the Eddington-Finkelstein time coordinate, satisfies the same characteristic equation with respect to a compactification of the tortoise coordinate as the one here on the right. So you want to preserve the characteristics, and then you want to switch from an unbounded coordinate to a compact coordinate, and that's what you get. So this is a horizon penetrating slicing of Schwarzschild event horizon. And of course, the metric is regular at r equals 2m. There is no problem here. And then we have Kruskal and Skeres in 1960. Again, it's a regularization. And at that time, people understood that the Schwarzschild black hole, that the event horizon was a one-way membrane. And here also you get hyperboloids. And the reason why you get these hyperboloids is because the r equals constant surfaces are hyperboloids. In fact, you see that the singularity is a hyperboloid itself. Now, this diagram is nice because it actually illustrates an important point about the Schwarzschild time, the fact that they intersect all at the bifurcation sphere. This looks very similar to the singularity of, let's say, the circular or spherical coordinates at the origin. They just intersect at this particular point. So this point is a singularity of the coordinates. And then we have Penrose, again, the same thing. At the bifurcation sphere, the standard time slices intersect. You get a singularity of these coordinates. And the Penrose diagram is constructed such that you get rid of this singularity. And if you look at it just to demonstrate, these are the slices of Penrose time, obviously, and they smoothly go across the event horizon. It only hits the bifurcation sphere at this particular point. So again, the point here is that in regular coordinates, you can clearly see that the bifurcation sphere is a coordinate singularity. All Schwarzschild time slices intersect there. And you can resolve this by switching to horizon penetrating coordinates from like intersecting slices to a nice smooth foliation, right? This is from t equals constant surfaces to Penrose time. Penrose t equals constant. So Penrose time is horizon penetrating. And you can see this with the other ones as well. I didn't draw an Eddington-Finkelstein diagram before, but if I focus on this shaded part, this is like the physical part, if you will, of Schwarzschild spacetime. You see that there's this intersection, and you switch to Eddington-Finkelstein or Paine-Lebesgue-Ulstrand is the same thing. What you get is this space-like foliation across this horizon. It's not easy to see that this is actually space-like, but if you plot the cone here, you can see that it's outside of the cone. And it's also important to note that this is a singular transformation, right? At the beginning, it was there was a lot of confusion by Hilbert and others, Singe, that the transformation should not be singular. Well, if you start with this singular coordinate, the regularization of the singular coordinate has to be singular. And it has to be singular in a way that your coordinate was singular. And in this case, at the horizon, it's a logarithmic singularity. We will see that at infinity, the structure of the singularity is different. But the point is that the coordinate transformation that you have to perform has to be singular in some way, in a particular way, I should say. Okay, so that was the black hole horizon. How am I on time? Good. And then you can do the same thing in the case of de Sitter spacetime, or in any like Schwarzschild de Sitter or any cosmological horizons. This is the de Sitter metric. Just like in the Schwarzschild case, you get a singularity at the cosmological horizon because this time that respects the Killing symmetry intersects at the well, here it looks like the origin, but this is intersection at the cosmological horizon, right? I don't think this point has a special name, not like the bifurcation sphere. I think it's because that point actually is observer dependent in certain ways, because de Sitter, is a homogeneous space. But the point is that if you use this t coordinate, they intersect at the cosmological horizon, and you don't want that. Now you can do the same game with a spatially flat construction. Surprisingly, this is due to Parikh in 2002. And you see that you get a spatially flat metric, and then here you get a different sign as opposed to the event horizon, because now your horizon is on the right. Right? You wanna have a smooth foliation across the future cosmological horizon, and then you go to Scri plus. Again, it's the same formula. Everything is the same. It's just cosmology instead of a black hole. You can also do characteristic preserving. This is, I first saw it in a paper by Missner in 2004. I don't know if anybody has done this before. Now, again, with a different sign, you demand that your unbounded coordinate at the cosmological horizon is mapped to a bounded coordinate such that your new time has the same characteristic form as your singular time. Okay, so probably you can tell where I'm going with this. This triangle is very suggestive of the Minkowski space. So we saw that, having horizon penetrating in the case of a black hole and in the case of a cosmological space has a similar structure. And now I will show that it's the same thing that what we do when we use our hyperboloidal coordinates at null infinity. It's not different. The geometry is slightly different, of course, but the causal structure is really the same. Here I have Minkowski space. This is the flat space-time. And you can see that spatial infinity is a coordinate singularity. So this is really how I view it. I mean, some people say that the conformal diagram, the conformal mapping squeezes the natural time slices in such a way that it looks singular. It's one way to put it. But if you're interested in the global structure, if you're interested in the causal structure, and if you're interested in following, let's say, describing waves, propagating waves in Minkowski space, not even gravitational waves. Of course, it's the same thing, but just simple wave equation. If you're interested in the global behavior of that energy and so on, then I think you have to regard spatial infinity as a coordinate singularity of the global structure, because the slices intersect there, just like they intersected at the bifurcation sphere or the cosmological horizon. And then the Penrose coordinates go through, of course, they hit the spatial infinity only on one slice, and the other slices give you a smooth foliation of the future and past null infinities, right? It's again a regularization of the spatial infinity. And it's not enough to go to null infinity, right? So there is a lot of literature about this Milne model that is due to Milne in 1933, who thought that this was an alternative cosmological model. It turns out that this is just Minkowski space in different coordinates. So in his coordinates, what he does is he takes the hyperboloid with radius tau and uses this radius as a new time coordinate. So now each of your hyperbola have a different radii. So these are pseudospheres with different radii, and you're using the radii as a time coordinate. And then the metric that you get has, again, this hyperbolic slicing, but it's time dependent. So this is a hyperbolic space, and these coordinates are very popular in like quantum gravity, ADS-CFT, and so on, because of the similarity of Minkowski space in these coordinates to ADS space. You get slices which have exactly hyperbolic geometry, so it's very appealing. But I think this is somewhat the wrong way to go about slicing Minkowski space in hyperbolic geometry, because your slices intersect at null infinity. So what you will have then is you will have things like energy conservation here, because at infinity, your slices actually do not move anywhere. This is, your metric is time dependent, your Hamiltonian will be time dependent. You're singling out the null cone that, goes out from the origin, even though the origin is not really a special point of Minkowski space, it's a homogeneous space, and so on. So I think this is not the right way to do it if you're interested in waves or global structure. A better way to do it is this hyperboloidal foliation. And this is, I think, due to Moncrief in 2000. I don't know if there are previous constructions that use the same thing, but the idea is to take this hyperboloid, right, to take the hyperboloids and shift them along the time-like killing field. And then when you do that, you get again the hyperbolic geometry on the spatial slices, and you get a nice foliation of future null infinity. The most important point, I think, in this construction is that the metric is time independent. And if you want to do numerical work, I think this is something that you need to do, that the time-like killing field is the same as your, its representation in your new coordinate is more or less the same. At least at infinity, you want to satisfy this property. Okay, so now I want to say something about the Penrose coordinates. Again, like the one that we have here. I started with the Milne and Moncrief construction because in case of the Penrose coordinates, we always are introduced in the Penrose coordinates through the null surfaces, where you compactify along the null directions. And I like this drawing of Penrose a lot because you can see here actually that the point at infinity, the spatial infinity and time-like infinities are really distinct, disjoint points of the space-time. The Penrose diagram is actually a little bit misleading in that regard. These points are separate, and then you get these cylinders, and this is exactly what the hyperboloidal coordinates do. They represent scry as cylinders with spatial cuts that have hyperbolic geometry, just like in the case of ADS. And when you look at what Penrose time actually is, when you decompactify Penrose time, then you see that this is really a hyperboloidal foliation. And it's a particular hyperboloidal foliation that combines Milne time with this time-dependent pseudospheres and the one that is shifted along the time-like killing field, right? So this is the way Penrose coordinates are constructed. If you want, you could start with hyperboloidal coordinates and compactify them directly, and you would get Penrose coordinates. Of course, this is an easier way to do it. It's also probably a better way to do it because because the null cone structure is really more fundamental than these hyperboloids in the space-time. But it's interesting that the nature of these coordinates is actually hyperboloidal because they do cross the horizon smoothly. So you can think of null infinity as another horizon, just like the cosmological horizon or the event horizon. And then when you say, okay, I want to regularize the coordinates that I'm using, so that I don't get intersections at spatial infinity. I get a smooth foliation. Then you have to use necessarily hyperboloidal coordinates. I mean, if you want time and space, of course, you can use null coordinates as well. But if you want time and space, then they have to be hyperboloidal. All right, and if you want to generalize this to, curved spacetimes with a time-like killing field, like black holes, Schwarzschild, de Sitter spacetimes, and so on, the way you do this is you define your time coordinates such that this is still satisfied. So your new time coordinate has to satisfy its time-like killing, has to respect the time-like killing field, and then you get a time-independent metric. This is very neat for numerical calculations, and if you need, you can compactify. And this is kind of where the conformal stuff comes in, right? So originally, I think in the hyperboloidal research, we started with the conformal structure, and that's fine, because Penrose diagrams and the Penrose method and Friedrich's seminal results on global stability of Minkowski space, they were all using conformal. But the way the conformal comes in is really due to the compactification in some way. If you map infinity to a finite domain, then this compression of infinite space into finite space requires that you conformally rescale the metric. But if you want to solve wave equations, you don't even have to use the language of conformal field equations. It's different for Einstein's equations, but the wave equations know somehow that they are conformally regular, right? So you can just view this as a coordinate transformation and then do your calculations. And just to make the connection to horizon penetrating, the same thing that Eddington Finkelstein and Painlevé and Gullstrand and Parikh and Missner did in the horizon case, you can do when you compactify. So in a way, compactification brings the problem home to you, because when you don't compactify, when you have these regular coordinates T and R, you don't see the problem. If you want to see the real problem at spatial infinity, you have to compactify, and when you compactify with this G, then you can construct a spatially flat gauge, you can construct a characteristic preserving gauge, or any other gauge. There are like millions of gauges you can do with it. Of course, you have an infinite freedom in your diffeomorphisms and what you want to do, but the point is really that regularity at infinity or at any null horizon forces you to a hyperboloidal foliation. So in that sense, it's really not like a magical niche thing. It's just comes out from the requirement of regularity whenever you have horizons. And you always have horizons because infinity is also somewhat a null horizon. So if you ask me, all this applied mathematics problems with wave equations, they should be using some sort of compactification, either along null curves or along hyperboloidal curves, to resolve the boundary value problems and so on that they have. And also mathematical analysis of wave equations, where you have energy conservation, which is, in my opinion, again, this is an opinion, I guess, it's not intuitive to talk about energy conservation in the case of wave equations, because you radiate the energy to infinity. The conservation is just a byproduct of intersection at non-infinity. Again, to really bring this point home, this construction of Rodrigo and Marcus, I like this a lot, the minimal gauge, because it really brings forth the point that regularity forces you to come up with a hyperboloidal foliation. So when you require space-like regularity at the horizon, so if you look at this metric, right, this guy here, anyway, you see my spotlight. So for this thing to be regular when F vanishes, or for this thing to be regular when F and G vanish, wherever they vanish, you have to fulfill the requirement that this FH has to go to plus minus 1. It's plus minus 1 because it depends on which side you're going and which direction you're going. Again, there are 4 quadrants. You can go to the future, you can go to the left, right, and the past, left, right. So the sign is determined by what you're interested in and where you're going, but it has to go to 1. And it has to go to 1 in a specific way that is determined by the asymptotic structure of this metric coefficient. And in the spherical symmetric case, it's just this F and the compactification that you choose. So when you require that this FH goes to 1 at the event horizon, and then it has to go to -1 at infinity, but then it has to be space-like. So the next leading order term for it to be space-like is this r² term. So you just put a constant there. Then you can take these things equal, and then you can calculate what this constant has to be, and you derive the minimal gauge. So this is a very minimal way of constructing regular coordinates across both horizons, the future event horizon and null infinity, interpreted as an horizon, as a null horizon, and then you get this minimal gauge, and that's how it looks like in the Penrose diagram. So this has been, discovered independently and separately, but people didn't really understand it until the work of Anzork and Macero. And even after actually they published their paper, I see this sometimes. Justin Ripley has 2 papers where he uses incur spacetime coordinates, which are essentially equivalent, not essentially, which are actually equivalent to minimal gauge, but they don't see it. So this is so fundamental that it appears even without people attempting it, and I like this construction a lot. Okay, so I think that was my talk, half an hour. We talked about hyperboloids, we talked about horizons, and how so the main point again, I'll just get to this. The main point again is that horizon penetrating time is hyperboloidal. Hyperboloidal is horizon penetrating, it's the same thing. You do not have to say horizon penetrating hyperboloidal compactifying, it's a mouthful. But structurally, it's really equivalent, and I don't know why it took so long for people to recognize that whatever you do at the event horizon to regularize it, it's the same thing that you do at null infinity to regularize it. And it just comes out in a natural way in Lorentzian manifolds. It's just a coordinate system, of course, it's not, new physics, but it's really natural, and I think it helps discovering new physics in many different setups, wherever you're interested in global structure and wave equations. So this is the talk, and I have one more slide, advertising. If you're interested in new physics, actual new physics that is discovered with hyperboloidal methods, we have a virtual infinity workshop in July coming up. We have about 20 registrations so far, so feel free to register. Thank you.